All right, welcome back, and we are going to do part two of the chapter one properties of gases lecture, picking up with diffusion and effusion. So diffusion is the process by which molecules of different substances mingle with each other, and spontaneous mixing of gases we know occurs naturally and is driven largely by entropic processes. So this includes atoms from solids as well, but that process is incredibly slow. You primarily are evaluating processes of diffusion in liquids and in gases. In the diffusion of a solid through a liquid solvent is possible as well, but because of speed of mixing, you're going to normally see much faster rates of diffusion in liquids and even faster rates of diffusion in gases. So diffusion accounts for the largely uniform composition of the atmosphere, and if a gas is produced by a localized source, such as, say, carbon dioxide being put off by a volcano, those molecules are going to diffuse rapidly throughout the atmosphere. And it's not just through diffusion, but also through active mixing of gases through motion in the atmosphere as well. So effusion is the escape of a gas through a small hole. And that's what we're seeing here with B. Let me grab my preferred device, okay? Whereas diffusion in A is the mixing of two different gaseous species in this diagram so that they're homogeneously distributed. B is effusion, and effusion is once again, the escape of gas through a small hole, like a puncture in an inflated balloon, for instance, or even just a really small pore in a balloon. So the rates of diffusion and effusion of gases increases with temperature, because, both processes depend on the motion of molecules, and molecular speed increases with temperature. So it makes sense that as temperature increases, we would see increased rates of both diffusion and effusion. But regarding the effects of molar mass, the relationship's simple only in the case of effusion, because in effusion only a single substance is in motion, not two or more intermingling gases, which you see in diffusion. So we're going to stick to the relationship of molar mass as it affects effusion specifically in the context of this course. Experimental observations on the dependence of the rate of effusion of gases on its molar mass are summarized by Graham's law of effusion, which was described in 1833. So it's been around for a little bit. And that law is that at a given pressure and temperature, the rate of effusion of a gas is inversely proportional to the square root of its molar mass. So what this means contextually is as molar masses increase, the rate of effusion will decrease. And as molar masses decrease, the rate of effusion will increase. So let's see what that looks like in a little bit more detail. Well, before we do the example, let's move on and talk a little bit about other aspects of effusion. Everyone here has had a balloon that's floating around, a helium-filled balloon, and noticed over time, even though it's contained within the balloon, it leaks helium and it slowly deflates and loses its buoyancy, starts to fall, and eventually it's just a partially inflated balloon sitting on the floor. And the rate of effusion of hydrogen and helium are particularly high because they're very small molecules. So what we saw on the previous slide was that the rate of effusion, like this, is proportional to the inverse of the square root of the molecular mass of the species. So we see that small molecules or small atoms are going to effuse much more quickly than large ones. So that's why you see helium and hydrogen especially moving through diaphragms so readily. Now for larger substances, we see different rates of effusion, and this is going to be something that you can actually utilize as a crude purification technique. And it's still utilized today, even though it's been around for a long time. So a great example is the separation of uranium-235 from the more abundant but less interesting uranium-238, making fuel for nuclear power plants. In this process, they derivatize the uranium to uranium hexafluoride, which is a volatile solid, and then they effuse them through a porous barrier. And the rate of effusion is going to be faster for the 235 versus the 238. But what we're going to see here is that because the ratio of the molar masses of the 238 to the 235 is only 1.008, and the relationship of the rate of effusion is related to the inverse of the square root, that means that the ratio of the rates of the effusion is only 1.004. So it takes thousands of successive effusions to separate uranium-235 from 238 via this effusion process. And this was used for lots of other processes as well, but now we have more sophisticated mechanisms of separation for determining separations in molar masses, for instance. Now, let's take a look back here at this problem, because I think this is a good problem to go through. You see that this question says, let's see, the rates in terms of amounts of molecules in which hydrogen, with a molar mass of 2.02 grams per mole, and carbon dioxide with 44.01 grams per mole, effuse under the same conditions of pressure and temperature are in the ratio described here. And you may say, okay, well, this doesn't look particularly tricky, but if you were to set this up yourself as part of a problem, you'd have to recognize that the rate of fusion of hydrogen on top shows 1 over the square root of the molecular weight of hydrogen. So the molecular weight of hydrogen is on the bottom. And then because the rate of effusion of the carbon dioxide is on the bottom, we have to put it on the top. And so when you're setting this kind of thing up, make sure that you're setting it up with an inverse proportionality in the relationship before you do your substitution. And then you can just take the ratio, take the square root of the ratio, and find what the relative rate of effusion between the two species would be. In this particular case, we find that hydrogen gas is going to effuse at 4.672 times the rate of carbon dioxide. And that's it for diffusion and effusion in the context of this course. Let's move along a little bit using some of these same concepts to discuss molecular collision as well as the rate of molecular collision. So the average distance a molecule is going to travel between collisions is called the mean free path, which is described by lambda. So let me stay here. Got a little lambda, mean free path. And the mean free path as liquid isn't going to be particularly interesting because those are in close contact with one another, although they're sliding about one another. But in the case of gases, gases have fairly long mean free paths where a molecule can travel several hundred different molecular diameters before having a collision with another molecule. And another way we can look at this is the term collision frequency, which is Rz. So these are collision frequency, and specifically what collision frequency is the average number of collisions one molecule makes in a given time interval divided by the length of that interval, so per unit time. So based on this definition, you can discern that the inverse of the collision frequency is the time of flight. So 1 over z is time of flight. And that's going to be the average time a molecule spends in flight between collisions. So we have a couple good working definitions to describe frequencies of collisions and distances between collisions now. Now, one more connection we need to make here is tying these concepts to RMS speed. So because speed is distance per unit time, RMS speed, c, which we remember, root mean squared speed, which we can generally think of just as average speed, even though we know that it's not necessarily mean speed, is the average length of the flight of molecules between collisions divided by the time of flight. And so that's how we end up with this first relationship, where RMS speed is going to be the mean free path divided by time of flight. And we see that's lambda over the inverse of z, and when it's an inverse of an inverse, we're just going to simplify this to say it's lambda times collision frequency, or mean free path times collision frequency. Now, that's pretty straightforward, but if we want to find an expression which includes both mean free path and collision frequency, we need a slightly more sophisticated version of this kinetic model. So the basic kinetic model supposes that molecules are effectively just points in space. And to obtain a collision, we need to assume that the 2 points physically collide with one another. And for that to happen, they need to come within a certain range from one another. And that's what we're seeing here with figure 111, is a description of what that range is. And in the context of this model, it's going to be this radius d, which is defined by the diameter of the molecule, which is then expressed from the center outwards, which provides a functioning radius of collision between 2 of those molecules with one another. So this can be described as a collision cross-section, which is sigma. And the collision cross-section is going to be just the circle, a 2-dimensional view of this sphere as they're passing each other on a single line. And that's going to be pi radius d squared. So it's pi r squared, except r happens to be the term d, which is the diameter of the molecule itself, expressed as a radius. So from this term, we can substitute in and see that our mean free path is going to be equal to the ideal gas law constant times the temperature divided by root 2 Avogadro's number divided by the collision cross section, which we see here, and pressure. Conversely, we can solve this for collision frequency by just substituting in the term z equals c over a lambda, which we see. And you might think, that looks a little bit complicated, but in terms of solving, it's actually not. We have all these tools in our toolbox already, so we know what the ideal gas law constant is, 8.314 joules per Kelvin per mole. We can find temperature in Kelvin. We can take the square root of 2. We know what Avogadro's number is, 6.022 times 10 to the 23rd units per mole. And then we just need to find cross-sectional collision cross-sections, and pressure. And collision cross-sections are defined here in terms of square nanometers. So by referencing this table, we have everything we need to solve for, in this particular case, mean free path lambda for any particular compound, in this case, in this example, oxygen, at standard atmospheric pressure and temperature, 25 degrees Celsius in 1 bar. Now moving back here, a couple important points. 1, because the mean free path is going to be proportional to the inverse of pressure, we see that mean free path decreases as pressure increases. That makes sense because pressure is determined by how densely packed gas molecules are with one another, and if they're more densely packed / more closely spaced, we expect them to bump into each other more frequently. Secondly, because mean free path is inversely proportional to the collision cross-section, the mean free path is going to be shorter for molecules with larger collision cross-sections. Also makes sense. Thirdly, because collision frequency is going to be proportional to pressure, the collision frequency increases with the pressure of the gas. Also makes sense. And because equation 1.19 listed above here shows that the collision frequency is proportional to the RMS speed, and we know that RMS speed is proportional to the inverse of the square root of the molecular weight, that means that heavy molecules have lower collision frequency than lighter molecules, providing their collision cross-sections are identical. So a couple important takeaways. So throughout the lecture so far, I've mentioned that these models are for ideal gases and that real gases behave similarly to ideal gases under normal conditions. Therefore, it's a reasonable model to apply to real gases in our normal day-to-day. However, there are some differences between real gases and ideal gases. And what are those differences? So everything we've said so far applies to these ideal gases, in which the average separation of the molecules is so great that they move independently from one another, meaning they don't experience intermolecular forces between the atoms, and the only interactions they have is purely through collision. So in terms of the quantities we've been using to describe the behavior of gases, a perfect gas, or an ideal gas, is a gas for which the mean free path lambda of molecule in a sample is much greater than d, the separation at which they are regarded as being in contact. So we need to have enough space in the gas, and we start to get behaviors that are non-ideal when the free path gets shorter and shorter and shorter, and the rates of collision and proximity start to increase, and then the inherent realities of molecules or compounds interacting with one another, both through attractive and repulsive forces, starts to occur, and you get deviations from this model based on its assumptions. So the result of this large average separation is that ideal gas is a gas which the only contribution to the energy comes from the kinetic energy of the motion, and there's no contribution to the total energy from energetic interactions which arise from molecules interacting with one another. But the truth is they do, right? So molecules will interact with one another. And there's two types of contributions that can happen to the overall energy of a system. When molecules are fairly separated from one another, but still within a proximity where they can interact, you see attractive forces primarily. So let me do a quick drawing for you guys. Let me see here. So if on this axis we have, y-axis, we have potential energy, and then we have separation along the x-axis, and we have, let's say, zero potential energy, defining attractive versus repulsive dominant separations, you're going to see something like this. That was not the best. Let me see if I can fix that. There we go. See if I can do something a little bit smoother. Where you're going to have a zone where they're very close, where you have repulsion, and everything after that line is going to be primarily attraction. And that's just because when you start to try to push electrons on top of one another, you have negative interactions, and they're going to strongly repel one another. But opposite of that, you're going to experience primarily attractive forces due to transient dipoles and weak force interactions, which are primarily attractive. So just remember that in the context of these models, there's limitations to how real gases will align with ideal gas models, and be cognizant of what causes those deviations and under what conditions we see those things happen more frequently. And overwhelmingly, it's going to be under high pressures where you have a lot of gas molecules packed in tightly with one another. Now, a couple important points. Molecular actions, including attractions and repulsions between molecules, do affect the potential energy that contributes to the total energy of the gas. So because attractions correspond to a lowering of total energy, as molecules get closer together, they make a negative contribution to the potential energy of the gas, as described in this collision model. On the other hand, repulsive forces make a positive contribution to the total energy, as the molecules get squished more and more together. So if there's any question about in which direction something may deviate from the ideal gas models, that would be an argument you would take into consideration. So molecular interactions affect the bulk properties of gas, and in particular, their equations of state. So the isotherms for real gases have shapes that actually differ from those that are predicted by Boyle's law, particularly at high pressures and low temperatures where the interactions are most important. So if we look at this figure 1.13, it shows a set of experimental isotherms for carbon dioxide, and they should be compared with the perfect gas isotherms that we see, say, in figure 1.1 previously. But we're going to go through these isotherms systematically and talk about where we see the deviations from predicted values under high pressures and low temperatures. And there's some very striking differences, especially below about 50 degrees Celsius and at pressures above about 1 bar. So let's take a look at some of these isotherms, starting with the 50 degree Celsius isotherm, the orange line on top. Now, in this particular experiment, you can evaluate the pressure of a system, in this case in atmospheres, as a piston is compressing a sample, decreasing the molar volume. And that's what we see along the x-axis. And as we move from the highest molar volume along the isotherm towards a lower molar volume at 50 degrees Celsius, you see a decrease in pressure, which corresponds nicely to what you would expect from Boyle's law. But let's take it down to, say, 20 degrees Celsius, our red isotherm. Interestingly, the critical isotherm is going to be 31.04 degrees Celsius for carbon dioxide, but we'll get to that definition in just a second. At 20 degrees Celsius, as we compress the sample with a piston, at first, between 0.6 and 0.4, heading towards 0.3 at point B, you see the same kind of continuous smooth change that you would see above, but with a slightly lower isotherm. But then at point C, we see a dramatic change. At point C, the variation of the pressure with the volume stops to move, and between C and D and E, you no longer see an increase in pressure as you are decreasing the molar volume. And what this indicates is an event of condensation, where the gas has been packed together so tightly that it has condensed into a liquid, and as we are pressing it together, it can no longer exert increasing pressure as this liquid is forming. And then between E and F, we have a very high pressure event associated with compressing a liquid. So we are actually experiencing phase change of the gas at 20 degrees Celsius, where we do not see that same phase change taking place at 50 degrees Celsius. Now, keeping your eye on, let's see here, jump back here, point D. So point D, smack in the middle of this flat feature. If we could look inside the container of the piston at point D, what we would see is a liquid which separates from the remaining gas through a very, very sharp surface. And at slightly higher temperatures, say 30 degrees, a liquid will actually form, but at higher pressure is needed to produce it. It might be difficult to make out the surface because the remaining gas is at such a high pressure that its density is going to be similar to that of the liquid, although it hasn't fully condensed to the liquid state yet. And at the special temperature of 31.04 degrees, or 304.19 degrees Kelvin, the gaseous state of the carbon dioxide appears to transform continuously into the condensed state, and at no stage is there a visible surface between the two states of matter. So, as we increase the temperature from 20 to 30 to the critical temperature of 31.04, we lose the definition between the two, and we're no longer in a liquid state and a gaseous state separated, but a single state moving continuously about under the same pressure. And at this temperature, this is called the critical temperature, or T sub C. And at all higher temperatures, a single form of matter fills the container at all stages of compression, and there's no separation between liquid and gas. So what we see here is that a gas cannot be condensed to a liquid by the application of pressure unless the temperature is below the critical temperature. If the temperature of the gas is above the critical temperature, no amount of pressure will condense it to the liquid form, and you enter a different type of phase. And this phase is called a supercritical fluid. So the dense fluid obtained by compressing a gas when the temperature is higher than the critical temperature isn't a true liquid, but it behaves a lot like a liquid and has density similar to a liquid, and it can act as a solvent very effectively, but over a more limited range of compounds. However, despite the density being similar to a liquid, the fluid's not strictly liquid because it never possesses a surface that separates from a vapor phase. So it can't go into vapor phase. And it's not much like a gas because it's so dense. It's just its own phase. It's a supercritical fluid. And supercritical fluids actually have a lot of really cool applications. When I was a kid, decaf coffee had a really bad rap, and I still poo-poo on it because, it's missing the important part, the caffeine. But the reason it got a bad rep was because coffee was decaffeinated using chlorinated solvents like chloroform. And chloroform was very effective at removing the caffeine from the bean, but it also removed a lot of other compounds that contributed to the flavor of the coffee. Now, commercially, that process has been replaced overwhelmingly with supercritical carbon dioxide. And supercritical carbon dioxide is very effective at removing caffeine as a solvent, but it's much more selective for caffeine than the compounds in the coffee that contribute to the flavor. It leaves a lot more of the rest of the coffee behind, and while taking out the caffeine. Another more modern example would be the use of supercritical carbon dioxide in the extraction of cannabinoids. And it's, interestingly, a very particular solvent when it comes to cannabinoids, and it's often used as a co-solvent with some alcohols. It's also prefers decarboxylated cannabinoids, not the acidic version of the cannabinoids. So it does function as a solvent, but it's much more selective than classic liquid solvents, and very, very interesting feature to work with. But in terms of environmentally interesting solvents, it's very, very appealing, because when you are done extracting at the supercritical phase, you just relieve the pressure. And when that happens, the supercritical phase goes to the gas phase. It off-gases, and when it off-gases, the gaseous state doesn't act as a solvent for the compounds that have been previously extracted, and those compounds literally fall out, and the gas evaporates off. So the step of removing the solute from the solvent is actually just a pressure change, which is very, very convenient. So a useful quantity for discussing the properties of ideal gases is a term called the compression factor, Z, capital Z, which is the ratio of the actual molar volume of gas, of a real gas, to the molar volume of an ideal gas under the exact same conditions. And that's what we're seeing in this relationship here, where Z equals the ratio of the molar volume of a real gas to the predicted molar volume of an ideal gas. And because we know, because of PV equals nRT, that the molar volume of a perfect gas is RT over P, we can rewrite the expression by substituting RT over P for the molar volume of the perfect gas, and get the following relationship, where the compression factor Z is pressure times the molar volume of the real gas divided by RT. Now, this relationship for a gas that's behaving perfectly is going to be 1, where Z equals 1. So any deviation of Z from 1 is a measure of how far a real gas is diverging from ideal behavior. And if we look at this figure 1.15, you can see on the axis we have, on the y-axis we have the compression factor centered at 1, and you get a nice flat line along that axis for 1 defining what a ideal gas would behave like. And then on the x-axis we have an entire range of pressures from 0 through 800 atmospheres. Now, you'll notice that not all gases deviate from ideal behavior in the same fashion. For instance, when Z is measured for real gases, it's found to vary with pressure. We see this. At low pressures, some gases like methane, ethane, and ammonia have compression factors which are less than 1. And that's what we're seeing here with methane, ethane, and ammonia all being under 1. That means that their molar volumes are smaller than that of an ideal gas, suggesting that molecules are being pulled together slightly. From this, we can conclude that these molecules, and under these conditions, the attractive interactions are dominant. That's what's leading to them being packed more closely together. Now, the compression factor rises above 1 at high pressures, which we see happening at around 400 for methane and ethane, but not for ammonia. And whatever the identity of gases is going to be true, it's just outside of the range of this particular thing, because if you pack them together tightly enough, at some point they will attract one another into condensations. But this type of behavior is going to be dependent on temperature. Now, what's interesting when we look at this graph, for hydrogen, you see that it's positive the whole time. The attractive interactions are so weak in hydrogen that the repulsive interactions dominate even at low pressures. So that's a very unique trend for the hydrogen where. And so when we look at the compression factor, we get some insight into what's dominating in terms of intermolecular forces at higher pressures. Is it attractive forces or repulsive forces? And at what temperature threshold do we see a shift in those effects? Now we're going to transition to virial equations of state. And we're going to go a little slow through this, but we only have, 4 more slides. So we're going to go a little slow through this, but this isn't actually as scary as it looks. We can use the deviation of z from its perfect value of 1 to construct an empirical, which is an observation-based equation of state. And this is going to be our virial equation of state. So to do so, we're going to suppose that for real gases, the relationship is going to be z equals 1, which is a reasonable assumption. And this is going to be only the first term of a lengthier expression, which then has terms which modify the behavior from ideal conditions. So this generalizable term we see here, where z is going to be equal to 1, that's our first term, plus b over v sub m, which was our second term, plus c over v sub m squared. So these coefficients, b, c, etc., are called virial coefficients, and b is our second coefficient, c is our third, and so on, and we can continue to add coefficients from b, c, d, e, f, etc. to further refine the model sequentially. And a is unwritten. A is the one term, by the way. So the word virio comes from the Latin word for force, and it reflects the fact that intramolecular forces are now significant. But we're not accounting for these forces specifically, we're describing them generally with these mathematical terms. So the virial coefficients, which are denoted B2, B3, etc. in place of BC, vary from gas to gas, and they depend on the temperature. And these are all measured for real gases. This technique of taking a limited expression, in this case C equals 1, which applies to gases at very large molar volumes, and supposing that it's the first term of a more complicated expression, is actually a pretty common approach in physical chemistry and other scientific modeling methods. So the limiting expression is the first approximation to the true expression, whatever that may be. And the additional terms progressively take into account secondary effects that the limiting expression ignores. So what that means is if everything behaved ideally, z would just equal 1. But we know that there's other things at play, so we have to start adding terms which give us improved predictive power, which are these virial coefficients, b, c, d, etc. So the most important additional term on this is going to be the one proportional to b. Because under most conditions, these smaller terms are going to be so small, they're going to be neglected. So as we move along this direction, the impact of the B term will almost always be more significant than the C term, will always be more significant than the D term, because they're going to be de-emphasized by the squaring of the molar volume underneath it. That's going to de-emphasize the magnitude of the effects of subsequent terms. So the most important term is your B term, the second, the C term, etc. That doesn't mean that we can't get further refinement from more terms. It just means that a quickly run out of significance in terms of predictive quality by adding more terms. Now, to convert this virial equation of state into a useful equation of state, what we're going to do is we're going to combine equation 1.21 with 1.20b, which is z equals pv over RT. And we're going to substitute this term for z, which is what we see here. Nothing else has changed. Then we're going to multiply both sides by RT over molar volume, and we're going to obtain the following expression, which predicts pressure based on these virial terms. And then following that, we're going to replace V sub n by volume per number of moles throughout, and get pressure as a function of N, V, and T. And now we have a nicely functional term. And what's really cool about this is in our first term, where we see z equals 1, that's assuming everything's behaving as an ideal gas. Well, we know that PV equals nRT, so really, pressure under ideal conditions is equal to RT over V. And then we just have a modifying term which refines the actual behavior of the gas under different volumes based on these virial terms, B, C, D, etc. It's a very, very straightforward relationship, a way of modifying and predicting mathematically deviations from ideal behaviors. So another type of relationship which we can use to evaluate how real gas deviates from an ideal behavior, other than these virial equations, is the van der Waals equation of state. And this is going to be leaning less on pure modeling and more on application of principle. So the repulsive interaction between two molecules implies they can't come closer than a certain distance. This makes sense. We can't physically overlap orbitals in non-bonding events. Therefore, instead of being free to travel anywhere within a volume V, the actual volume in which a molecule can travel is reduced to an extent proportional to the number of molecules present and the volume they each exclude. So we can therefore model the effect of the repulsive volume excluding forces by changing the volume in the perfect gas equation to this new expression, V minus NB, where B is the proportionality constant between the reduction in volume and the amount of molecules present in the container. And you can see derivation in the book, but we're not going to go through the derivation specifically here. So far, the perfect gas equation or ideal gas equation of state changes from PV equals nRT, or P equals nRT over V, to the following, where we substitute V for V minus NB. That's the only difference. So this equation of state, which isn't yet quite the full van der Waals equation of state, should describe a gas in which repulsions are important. So we've only included repulsions so far. So note that when the pressure is low, the volume is going to be large compared to the volume excluded by the molecules, right? So under those conditions, there's going to be very little change in predicted pressures between this new equation and the unmodified PV equals nRT. But as the pressures increase and the volumes decrease, the excluded volumes based on the number of molecules and the proportionality constants are going to become more and more and more impactful. So the effects of attractive interactions now between molecules is to reduce the pressure, because if they're attracting one another, they lose that kinetic energy of them bouncing around, because they're actually taking away that kinetic energy, kinetic potential energy of the gas. And it's going to reduce the pressure the gas exerts on whatever its container has. So we can model this effect by supposing that the attraction experienced by a given molecule is proportional to the concentration, N divided by V, of molecules in a container. Because the attractions slow molecules down and the molecules strike the wall less frequently and strike it with weaker impact, we see reduction in pressure. We therefore expect the reduction in pressure to be proportional to the square of the molar concentration, one factor of N over V, reflecting the reduction in frequency of collision, and the other factor, the reduction in the strength of their impulse. Impulse being a collision with a full bounce back. If the constant of the proportionality is written A, we can write the following, where the reduction in pressure equals A times the square of N over V. So we can now take this term and combine it with our modified statement of pressure, because it's a reduction in pressure, and just subtract it from our newly predicted pressure. So now we have a term which is allowing for both repulsive forces and attractions. And it's rewritten here for reference. So this expression is our van der Waals equation of state. And to show the resemblance of this equation to the perfect or ideal gas law, P equals nRT, is sometimes rearranged by bringing the term proportional to A to the left and multiplying throughout by V minus NB. So, whereas we would normally see PV equals nRT, now we have a modification to the P term and a modification to the V term. So what's really slick about the van der Waals equation of state is it's built using physical arguments about volumes of molecules and the effects of forces between them versus just a purely mathematical modeling, including new terms which give us the ability to describe behavior of a gas, of a real gas, without rationale. This actually includes some rationale as part of the modeling process. What's also nice is that we have these van der Waals parameters of gases well documented now, table 1.5 here, where we have A terms and B terms for whole air, ammonia, argon, carbon dioxide, etc. as you go down the list. Now, these van der Waals expressions, A and B, these parameters, depend on the gas. So they're dependent on each gas because how each gas deviates based on its relative amount of attraction or repulsion varies from real gas to real gas. But they're independent of temperature. So they actually apply over all temperatures, which is excellent. And we can judge the reliability of this van der Waals equation by comparing isotherms that it predicts, which are in figure 1.17, this first figure, with experimental isotherms that we've already shown in figure 1.13. And apart from waves below the critical temperature, where we get phase changes, which aren't accounted for in this, they really do a good job of modeling experimental isotherms to very, very well. So these weird waves that are included underneath, these guys here, are called van der Waals loops, and like all models, there's limitations to models. These loops are unrealistic because they suggest that under some conditions, compression results in a decrease in pressure, and that's just not feasible. So these loops are almost always trimmed away and replaced by horizontal lines in the areas they aren't applicable, and that's what we're seeing in figure 1.18. So there's two important features of these van der Waals equations that should be noted. Firstly, perfect gas isotherms are obtained from van der Waals equations at high temperatures and low pressures. That's excellent. To confirm this remark, we need to note that when the temperature is high, RT may be so large, the first term on the right of the equation, 1.123, greatly exceeds the second, so the latter can functionally be ignored. And furthermore, at low pressures, the molar volume is so large that V minus NB can be replaced with V. So under those conditions, high temperature, low pressure, the van der Waals equation really reduces to P equals nRT over V, which is the ideal gas law. And secondly, well, actually disregard that. We actually don't need to go into the relationships between critical volumes as applies to van der Waals. So I think the big picture is more applicable here. And that's going to be it. That's it for Chapter 1. I'll be putting together a Chapter 2 sequence of lectures, but I think this has more than enough information to get everybody started on working through the homework sets. See you all in class, and we'll go through some of the problems.